travels around the world, and I'm asked, why Sinetamer? What is so special? What is so unique about your surge suppressor as opposed to the hundreds of others that are on the marketplace? What I'd like to do for the next few minutes is address that very point and discuss part of the issue of the necessity for a redesign of a surge suppression device, the unique technology of Sinetamer and how it can positively impact your facilities. Our job is protecting electronic infrastructure around the globe. So please, watch with me. Hello, Jeff Edwards here. I'd like to spend the next few minutes discussing energy control systems and Sinetamer with you. You know, for over 25 years now, the electrical power quality industry has been my life. As of late, I travel almost 200 days per year around the globe discussing and talking about our technology, talking about Sinetamer, discussing how what we do can provide a positive benefit for your company. So what I'd like to do is discuss this technology and how implementing it and deploying it throughout your facilities can provide many times up to a 60 to 75% reduction in operating expenses. In order to do this, though, we must make a shift or a change of our protection philosophy. You know, it's very easy for me to make you change a lot of things. I can make you change your shirt, I can make you change your shoes. However, I cannot make you change your mind. It is something that you must choose to do. We have to change our philosophy in surge protection from just protecting the electrical equipment, the electronic, the main service entrance. We must shift to start talking about protecting electronics, protecting microprocessors, providing software protection. Why do we need to do this? Well, very simply, everything has optimal operating environment. Some things are very complicated, why you can see it from the formula here, but our electrical equipment has an optimal operating environment. And even though electricity has changed very little over the last 100 years, the necessity for pure sine wave, as you see, has changed radically. If we provide our electronic equipment with such a sine wave, then everything is going to function very nicely. This is a type of electrical sine wave you see as the electricity leaves the generating station or is found in many laboratories. It is this type of sine wave where companies such as Siemens, Allen Bradley, and ABB design and produce their equipment. However, we take it from this very sterile, clean environment and we introduce it to an environment that looks like this. Thanks to variable frequency drives around the world, many other switching events, we now have a sine wave that looks like this. And so all of the investment we've made into this ultra-sensitive, high-performance electronics for packaging, processing, telecommunications, whatever, is now put into an environment that it was never designed to operate in. And so the ideas and the objectives of obtaining extra throughput or more production falls to the wayside because of what we have here. Why is a different technology necessary today for surge protection? Well, it's very necessary because 21st century electronics demand a different sine wave. It demands a much tighter tolerance. Let's look at what has happened over the last couple of decades with computer chips and microprocessing. As we look back into the 70s and 80s, we see that the microprocessors were operating in the low 10, 25, 30 megahertz. I recall when we began our company in 1987, we had a 25 megahertz system with a 40 megabyte hard drive. Now, our cell phones have more than that. Now we're operating with quad core processors in the gigahertz range and higher. It's very difficult to even keep up with the speeds these days. At the same time, the operating voltages on these chips and microprocessors have steadily decreased from a high voltage of 24 volts down to the microvolt level, thus increasing the necessity for a tighter tolerance on the sine wave. If we look at it graphically, we can see that at the slow processing speeds, those 400, 500, 600 volt transients or spikes or surges had very little impact to no impact upon the operation. However, as the microprocessing speed increased, now you can see some of those transients exceeding the peaks of the processor, thus causing disruption. Not necessarily catastrophic failure, but disruption. Now in the 21st century, in 2014, those same transients have much greater possibilities and probabilities of disrupting microprocessing, disrupting packaging, causing resets, causing lockups, which have no explanation. It just becomes, oh, we must reset it. However, there's a solution to that. The solution was, let's design in or provide surge protection. Well, let's look at that technology as it has evolved. We see the clamping levels represented by the red lines above and below the sine wave. At these points, anything below this point, nothing occurs by the surge suppressor. However, once a transient or a spike exceeds the peak of that sine wave, then the suppressor, the elements, lower their impedance and begin to clamp that transient. As you can see by the black X's, we're clipping off or clamping events that go over those peaks of the sine wave. However, inside the sine wave, you can still see other events. Now, as I said, these will not cause catastrophic failure. Over time, they create stress on the chips as well, but they create disruptions. It's only by implementing a technology that could actually monitor the frequency of the sine wave, because a transient is a change in that fundamental frequency. Can you receive the total benefits of your electronics? This is what we call our frequency attenuation network. Sinetamer has designed what we call a 4th generation surge suppressor. It attacks the very nature of the problems that disrupt electronics and cause software confusion. How does this technology work? It's not a mystery, but it is very special. If you look at the graph here, you can see the green line, which represents the switching transient, the 100 kilohertz average switching transient. As that transient reaches its peak, you'll notice the red line. That red line represents the attenuation network. As the transient builds, the red line represents the clamping or the attenuation. So at the very maximum peak of this switching transient, we are suppressing at the maximum level. As the transient rings down or oscillates down, the need for our frequency tracking or frequency attenuation becomes less and less. So you can see it's an inverse relationship. The higher the peak, the greater the suppression. If you'll notice at the very end of that green line is in the megahertz range. This is typically non-disruptive or destructive to microprocessors. Now, the other two black lines that are between the green and the red line represent the function of the metal oxide resistor, which is the most common suppression element. If you'll notice, it very slightly impacts that green line. So where MOV type technology is necessary for energy handling and for lightning protection, it is a very, very little benefit in terms of protecting electronics. We have a number of engineers that say, well, isn't that just EMI RFI filtering? And that's an excellent question. However, the EMI and RFI filters are operating at a range that are outside of the range of switching transients. They are operating in the megahertz time frame. Those create issues that are very peculiar and specific to certain industries, but they don't cause microprocessor disruption. If you look at the graphs here, you can see that it's an inverse bell curve. And the graph on the left represents our frequency tracking, which is in the 100 kilohertz time frame. The typical EMI RFI filter is out in that megahertz time frame for its optimal operation. So on a data sheet where you see EMI RFI filtering, that does not represent true frequency tracking. So practically speaking, what kind of benefit can this provide? Well, if we look at the sine wave, it is just like a computer language, ones and zeros. Ones being at the peak, 0 at crossing, and then a -1, and then up to 0 crossing again. As long as all of those ones and zeros are in the proper place, the function from the microprocessor side is perfect. Well, we hope it's perfect. However, what happens due to the implementation of variable frequency drives and other switching events, now those ones and zeros can become corrupted. Once you get transients at that zero crossing, you no longer have the 1 0 1 0 that can be processed and translated to the DC circuit. Now you have 1 1 1 1, which as it continues can cause a disruption, can cause a lockup, can cause a ghost change in what's happening out on the processing or the assembly line. The typical suppression device that is implemented around the world will only impact those events that go over the peak of the sine wave, as you see by the red lines. And so, in many discussions, engineering teams and managers will say, you know, we have attempted to use surge protectors and they really do not work. This is why. This is not the fault of the suppressor. It could only do what it was designed to do. However, with our frequency attenuation, we can now radically eliminate, radically reduce, practically eliminate those false zero crossings, so that as that sine wave is processed and the information goes into the microprocessor, it's pure and clean. This graph here you can see represents a study that was requested by our team many years ago, and it was on a food processing line. These transients are no more than 600 or 700 volts maximum, and they were causing no computer or no equipment failure. Various manufacturers were called in to look at the sine wave, talk to the engineering team. They had no answers. As we began to look at the sine wave, we noticed that as that sine wave crossed zero, because of the switching events, there were 9 different zero crossings of that sine wave. So as that controller was counting and processing, all of a sudden they received 7, 8, 9 different zero crossings. It became confused and said, I'm checking out. Only when it was reset was the line able to move again. The top left-hand graph represents what was happening before. The second-hand graph on the right side represents what happened after. With a system, a cascaded approach to utilizing our products inside that assembly line, their production continued smooth from there on out. I want to thank you for the opportunity just to share with you just a snippet, just a little bit about our technology. We are technology for the 21st century. Our job around the world is protecting electronic infrastructure. You rely upon it, you depend upon it, your clients and customers depend upon it. And we are here for you to provide a vast array of potential products for you to implement into your facility. The implementation and deployment of Sinetamer will provide a return on investment, many times up to 80 to 90% reduction in equipment malfunctions and board failures. I invite you to go to our website for additional information, www.sinetamer.com, or contact us by email for additional information. We will have someone contact you immediately, and very likely we have a distributor, factory representative in your area. Thank you.